All right, so today we're starting into the quantum mechanical model of the atom. And we're up front here going to be talking conceptually about a lot of things, and then applying some equations that you'll get on the exam, but you'll need to know how to use them. Constants you'll be provided, but again, you need to know how to use them. Oh, and this is always a fun quote from Niels Bohr, right, from the Bohr model of the atom. Anyone who is not shocked by quantum mechanics has not understood it. Quantum mechanics is really weird. And a lot of times if you ask, oh, why is something this way? And it's like a deeper level question, a lot of times the answer is quantum mechanics. And you don't really want the answer because it gets weird and it gets really math heavy. The beginnings of the quantum mechanics was basically until the 20th century, it was believed that physical phenomena were deterministic. Does anybody know what that means? What does deterministic mean? You can determine it. For example, if I threw something across the room, from where I threw it, you could predict where it's going to land on the other side of the room, how fast I throw it, that kind of thing. So it's where it ends up is determined by the amount of energy, its starting position, the direction that I throw it, all that kind of stuff. So basically everybody believed that everything was deterministic because at the level that we can see things, it is. That was until they started looking at these subatomic particles and realized that actually for things that are really small, they're not deterministic. So if you shoot an electron down a path and measure where it lands, you could shoot a second electron after it and it will not land in the same spot. So the path, the direction that you throw something, or the velocity that you give it, the angle, all of those things do not determine where that final particle ends up, down at the very small. So it's called probabilistic. The absolutely smaller quantum world of electron behaves differently from the larger macroscopic, which is weird because it's these really tiny things that make up the really big things. So at some point, there's a transition from probabilistic to deterministic. And this is actually the part of the quantum realm that, like, the Marvel universe has gotten right. It's just weird. You can't really predict what's going to happen. There's some general things, but it's just weird. Everything else is wrong. So when unobserved, you can treat small particles like electrons to be in two different states, so doing two different things at the same time, until you observe it, and then it becomes one or the other. Very weird. Like, electrons are incredibly small. So when we're talking about these things, we're talking about the very, very small. Oh, I looked this up earlier, and I don't remember if I actually saw what Google said. Yeah. So a single speck of dust has more electrons than the number of people who have ever lived on Earth. The number of people ever lived on Earth, assuming that this generative response, oh, there's an actual sort of response. 117 billion humans that have ever lived ever. So really, there's more electrons in, so there's more electrons in a single speck of dust than all of the humans that have ever existed, which is a lot of electrons. And we can't directly observe electrons in the atom. We can determine either their position or their velocity, and we'll talk about that more later. And if you think about what does it mean to even see something, I haven't really talked about this yet, right? The thing that you actually see, the thing that our eyes pick up, is electromagnetic radiation, in the visible spectrum at least. So if I shine light on an electron, that automatically changes the state of the electron. So it's so small that even the process of viewing it changes it. So Schrodinger's cat is a little bit misunderstood. It's a thought experiment. Nobody actually took a cat and put them in a box with poison. But the idea was that if you took a box and then you put a radioactive element in there with the cat, hook that radioactive element up to a poisonous gas, and then close the box, then the radioactive particle could either emit or could decay and emit radiation and release the poison and kill the cat, or it wouldn't. And the only way you would know was by opening the box. Of course, that's not really the case. Whether or not we open the box, the cat either dies or doesn't die. But we don't know anything until we observe it. And as soon as we observe it, then we know what it is, and we collapse all the possibilities into a single sort of reality. So nobody ever did this to a cat, but the idea was that this cat could be dead and alive at the same time is really weird. And it was to highlight that these things that exist or these properties of the quantum sort of realm, these really small things, is very different from the macro scale that we observe every day. Oh, it'd be like radiation connected to a detector, and so if it detects radiation, then it would release the poison. Yeah, so not that the radioactive element directly would kill the cat, but radioactive decay is random and there's a probability to it. And it might decay right now or it might decay later. You can't really determine when. Yeah, and that's why Schrodinger wrote, I don't like it and I'm sorry I ever had anything to do with it. And Albert Einstein really wanted to disprove the thing that he brought into existence. He was the one who did a lot of the work on quantum mechanics. And he's like, I need this to not exist. And he was not able to prove that it did not exist, or that was not the way things were. So if you download these slides, you can find those videos. We're not going to take time with them now. Okay, so a theory that explains electron behavior. So there were a lot of things that scientists observed about electrons and electron beams that was weird. And so they needed a model, quantum mechanical model eventually, to be able to make predictions about how different elements would interact. Because if you can predict the properties of atoms, then you can predict the properties of materials, and we can build things like space, or we can build high-tech materials, even like your phone or iPad screens, or very high-tech materials that require an understanding of quantum mechanics in order to operate. All of the silicon chips are the same way. So a lot of technology was unlocked from this. And these properties of atoms, again, these electrons really tell us why some elements are metals and others are nonmetals, why they gain different numbers of electrons or lose different numbers of electrons, why are some reactive while others inert. So it tells us a lot of things about atoms if we can predict the way that electrons behave. So one of the first things we've got to talk about then, to really get into these concepts that you need to know, is that light is a form of electromagnetic radiation. So I don't really talk about this in Chem 20, but electromagnetic radiation, it's got two parts, right? It's got electro and magnetic. And so an electromagnetic wave is a magnetic wave and an electric wave that are perpendicular to each other and self-propagating. So if you have a phone that has wireless charging, right, you can put your phone on the wireless charging pad. The wireless charging pad creates an alternating electric field, which creates an alternating magnetic field, which then interacts with the coil in your phone to create another alternating electric field. Electromagnetic waves, or electromagnetic radiation, I should say, is that, but happening in the air. So the Wi-Fi signal, it's being created by some oscillating electric field, which around it creates an oscillating magnetic field, which in the air generates a perpendicular wave of perpendicular electric wave. So two things exist doing this thing through the air. So it got two parts to it. And we really just talk about it as one whole thing because they exist together. So yeah, electric field and your magnetic field. And then as long as electromagnetic waves or radiation is moving through the same type of substance, they have the same speed always. We usually talk about the speed of light in a vacuum. The speed of light is 3 × 10⁸ meters per second. For a little perspective, I actually calculated this earlier today, rode on the bullet train. Bullet train goes 170 plus, it goes a little bit faster for some trains, but I was going 170 miles an hour on the bullet train. That's about 75 meters per second compared to 3 × 10⁸ meters per second, or 186,000 miles per second. And this is in a vacuum. So the speed of light changes, but only depending on what it's passing through. You generally treat it as constant. So this is a picture of what an electromagnetic wave looks like. So you got the one wave here, the electric field component going up and down, and then left and right or into and out of the screen is the magnetic field component. So as one increases, the other one increases, and then as it decreases, the other decreases, each one sort of making the other happen. Oh yeah, you experience this, the difference between the speed of sound and the speed of light whenever you see lightning, which actually recently had some lightning, with all of that hail. It was a lot of hail. So the speed of light, 3 × 10⁸ meters per second, and that's why when you see a lightning flash before you hear it, because the speed of sound in regular air is 340 meters per second, which is a whole lot slower. And so you could use that and figure out like how many seconds after you see the flash, because the flash is going to be essentially instantaneous. This is also why it doesn't matter really how fast you're going in your car or if I'm on the bullet train. Your cell phone can still send signals to the tower and have them come back and reach your phone, because the distance is essentially doesn't matter. Electromagnetic radiation go around the Earth in a matter of seconds. Huh?
Sending a signal is like sending a light.
It is sending light.
Okay, so that's the whole, it's a wave and a frequency.
Yeah, and I guess more accurately it would be electromagnetic radiation is what it's sending. Light is a subclass of that.
So like the electrical shields, like they're not like this.
Right. Yeah, so we'll talk about what makes them higher energy or lower energy. And actually we'll talk specifically about like how much energy it takes to really affect a substance. So there's a few things that you need to know about waves, ways to describe them. One is the amplitude. So amplitude is the height of the wave, or sort of the intensity of the wave. And these are measured as two similar points on a wave. So either the highest point to the highest point, the lowest point to the lowest point, or this 0 point to the next 0 point. The easiest way to do it is crest to crest. And then the amplitude is how far this comes away from what is 0. So you think a wavelength is the length between waves, or the distance between alternate nodes. Amplitude is not one that we talk very much about in this class, more than in Chem 20 though. So the thing that makes different colors is the wavelength. The amplitude determines the brightness. So you can have a really bright or a really dim red, yellow, or blue light. Red light's going to have a longer wavelength. Yellow would be a little shorter. Blue would be even shorter. And for colors, it's usually measured in nanometers. So amplitude is how bright, wavelength is the color. If we're talking about colored lights, at least. Okay, the last one you need to know is the frequency. So this is the number of waves that pass a point in a given period of time. So if I've got a fixed point, that's terrible. I can do better. There we go. If we've got this wave and we're measuring the number of times that it passes this fixed point, the wave always moves, again, speed of light is essentially constant, so it's always moving at the same speed. So as this passes through, whatever speed it's at, however many peaks cross per second is what we usually use, is the frequency. And so for different wavelengths, you can have different frequencies. So if I draw a really long wavelength, longer distance between crests, those move though at the same speed. So in the same time that it takes my low wavelength wave here is like 1, 2, 3, 4. We get 4 crossings per second, let's say. And then for the other wave, it's only going to be 2 in that same amount of time. So frequency is related to wavelength. Since they're always moving at the same speed, if I've got a short wavelength, that means I've got a lot of waves crossing every second. If I've got a really long wavelength, right, the distance between peaks is a lot longer, so I'll have a fewer number of waves per second. So you can think of also these, you can think of these as waves on a beach almost, right? If there's a shorter wavelength, that's like a shorter time between waves, so they're striking with higher frequency. You could also change the height of the waves, as there's taller waves, then that's essentially the more force that one wave has. So partial analogy though, as we'll see. So frequency and wavelength are inversely related. Higher frequency, larger frequency, higher frequency means a shorter wavelength. Oh, and I didn't talk about the symbols for these. For frequency, it's nu, which is essentially a V. Usually it's like it's got like a little wing on the left side. And then wavelength is, it's there, but it's also here, is lambda. Lambda. Just keep those in mind. Ah, cool, that's what I meant. Again, for waves traveling at the same speed, electromagnetic radiation, they're all going to be traveling through at the same speed through the same medium. The shorter the wavelength, the more frequently that peaks pass. Yeah. If you pass light through a different substance, the speed of light does change a little bit. So light travels slower through glass than it does through air.
Will that change the wavelength or anything?
And it changes the wavelength too. The frequency is, because the frequency stays the same. That's a physics question. That's physics. Yeah. We could do some stuff, but because the speed of light, again, we're treating the speed of light as constant, or at least as the same in the same material. So we're talking about different frequencies of light in the same medium, so in air or in space in a vacuum or through glass. So we know the wavelength, then we can find the frequency. And again, nu is frequency, lambda is wavelength, and c is the speed of light. All right, so color is determined by its frequency or its wavelength, because remember, again, they're related. Usually it's talked about in terms of wavelength. So if you buy laser pointers, they'll give you the wavelength in nanometers. White light is a mixture of all colors. Actually, these fluorescent lights, depending on what they're made of, might be missing a few colors, but for the most part, they're all colors. So red, orange, yellow, green, blue, indigo, violet, Roijibiv. And then when an object absorbs some of those wavelengths and reflects others, it appears as the color that's reflected. So if you see something that's red, it's absorbing every color except for red. If you see something that's green, it's every color except for green. If you see magenta, then your eyes are lying to you. And it's red and violet, but that's a different thing. And so here's the electromagnetic spectrum. So light, as I said, was a subset of that. It's really just a small band of the electromagnetic spectrum. So on the long wavelength side, the low frequency, we've got things like AM radio, regular TV. This is not like, this would be like the antenna TV. FM radio is in that range. Cell phone is in that range. And actually probably even expanded a little bit more into the shorter wavelengths. So you've got things like millimeter wave, 5G, which is like the super fast cellular internet, and then infrared light, which you most of the time feel is heat, visible light, and then ultraviolet. And infrared and ultraviolet are named based on where they sit with respect to the visible colors. All right, so infra, I-N-F-R-A, infra means lower than red. So lower frequency than red is infrared. Higher frequency than violet is ultraviolet. And then things get higher in energy from there. You got X-rays and then gamma rays, which are like the highest energy. So like you can get sunburns from ultraviolet light. Visible light obviously is fine. Then infrared is generally felt as heat emitted from objects. So all objects give off a small amount of infrared light as from heat. And then microwave, which microwave, the only reason that microwaves, does anybody know why microwave is able to heat up your food? Yeah, specifically it resonates with, or I guess I should say, specifically water molecules resonate with that range of radiation. And actually, this is my fun story about microwaves. Does anybody know how the microwave was invented? Yeah, he walked in front of a radar dish. So they used microwaves for radar and like satellite dishes pointed at space. He had a chocolate bar in his pocket, walked in front of it, and it melted the chocolate bar in his pocket. Then they were like, oh, that's really interesting. What other things can we heat up? Do you know what the next thing they heated up was? Yeah, it was hamsters. So at that time, when they like discovered microwaves heat things up, they were also trying to figure out, can we put people into like cryosleep? If you've seen Futurama, he goes into cryosleep, they freeze him, and then gets thawed out later. So while they were doing that, they're like start with really small mammals and start working their way up. And so they were doing this with hamsters. And so they were trying to bring these hamsters back without hurting them. And so they were trying things like warm or hot water. They tried just like basically a gentle convection oven, heating them up, but trying not to give them burns. And that's when the first like tabletop microwave was invented, was to thaw hamsters. Huh? No, I mean, you don't want to tumble them. But yeah, like a dryer is essentially a low heat convection oven for your clothes. So they basically invented this tabletop microwave to thaw hamsters. And that did a better job of thawing hamsters. Now we don't have cryosleep available now because the problem is you get too big and then too many cells get damaged and you just don't survive. Still, some people before they die, they get frozen just in case eventually they figure it out. Who knows? But that being said, microwave only works because it resonates with water molecules. Lower energy than infrared. So that's why microwaves, cell phone signals, they basically pass through your body without interacting with anything. So that's the whole electromagnetic spectrum. Huh?
Metal in a microwave?
Oh, metal in a microwave? That sounds like another physics question. I can find a YouTube video for you. It does have to do with exciting the electrons in the metal, which are free flowing. And then you only really get sparks if there are jagged edges. And then it arcs over the jagged edges. Did it explode?
It's too little to understand.
Oh, yeah. My one of my brothers, when he was really little, put a can of butane in the microwave and turned it on. Unfortunately, it did not explode and blow up the house.
Because the aluminum was frozen and I thought it would just be.
Oh, yeah. No.
And then I saw the lights and everything and I was like, oh.
Most metal things are kind of okay. Like if you put a spoon in there, if you put a fork in, that's more likely to cause problems.
Like a burrito wrapper.
Yep. But if it's crinkled, yeah. Yep. All those crinkly spots is it where it jumps. Anyways, it's fun to talk about ways to destroy microwaves. So if we're going to arrange colors though in terms of their energy, we got red, green, and blue. So red, green, or blue, which one has the longest, what does it say, in order of increasing wavelength? So the shortest wavelength. Yeah. Wait, sorry, wavelength. If we're talking wavelength, these are the wavelengths in nanometers. The shortest wavelength is, yeah, blue. Got to remember which way we're going here. Blue. And then green. And then red. All right, now that we've got one of these down, we should be able to figure out the rest. So in terms of frequency, which one's going to have the shortest frequency? Who thinks it's blue? Who thinks it's green? Who thinks it's red? For shortest frequency. Yeah. I guess shortest frequency, I should say maybe smallest frequency. How many times is crossing? Yeah. Here, let's do it like this. So if I have all of those and they go past a line altogether, which one's got the lowest frequency? Or the lowest number of amount of times crossing per second? Yeah. Red, green, and blue. Now what about energy per photon? Lowest, so we're going in order of increasing. So lowest energy first. So if we look at the wavelengths maybe, because these are all related. So a shorter wavelength is higher energy. Oh, and already like they'll do this. Shortest wavelength is the highest energy. No. Highest frequency is the highest energy. Mm-hmm. Because the red is the longest wavelength. So the longest distance between two waves. How many times it crosses per? So more waves in the same space. Higher frequency. So red is lowest energy. Green is always in the middle. Blue is highest energy. So frequency and energy always match up. A low frequency is low energy. A high frequency is high energy. And wavelength's the opposite. Okay.
The frequency, the waves, like the more times it's hitting, then it's gonna have like more energy.
Yeah, yeah. If you think it's hitting more times per second, that's more energy. Nope. Physics. If they're all in the same material, it's, again, I'm just going to say physics. So we're not going there. Yeah, if they all pass through together, it doesn't change. But again, we're not. They got to answer the question, what if they pass through different materials? Not answering that question. I don't know how to answer that question. Just introducing some basic concepts of waves, really. Okay, so this is another thing we need to know about. This is interference. So if you have two different waves, you can either have constructive interference, which means that they're in phase, which means that they stack on top of each other, or you can have destructive interference, which means that they are out of phase and they interact to cancel out. This is how noise canceling headphones work. Which, another fun story about that, I don't know, maybe it's a fun story. I don't know, Mr. Bose, the guy who invented Bose, he's the guy who invented the first algorithm, at least, for noise canceling headphones. And he did that because he was on an airplane and he was really annoyed by the sound of the plane. Now, he did that before we had computer chips and software that was fast enough to run his algorithm in real time. So he wrote it like on paper before it was possible. And then eventually it was made possible. But in noise canceling headphones, you essentially have your headphones creating a sound pattern that is the exact opposite or exactly out of phase with the unwanted noise that's coming in. So this is why airplane sounds are really easy to cancel out, because they're very consistent and they don't change very much throughout the course of a flight. Other things like sharp noises or even voices are a lot harder to cancel out because they change a lot. And so the algorithm or whatever has to match that basically in real time. Constructive interference would be like your noise canceling headphones not working and then amplifying the sound of everything that you did not want to hear. So it would make airplane sounds louder because it would be adding the frequencies on top of the airplane sounds that already exist. So waves can either stack on top of each other or cancel out. And here you can see the amplitude is what gets added. So we've got two waves here that are approximately the same height, but when added together, their height or amplitude is doubled or added together. When they're completely out of phase like they are here, then the result is nothing. Of course, these are like perfect sine waves. Usually they're more complex. All right, so diffraction is what you get when you have two waves traveling in kind of the same direction around an object. And one of the keys here is that the obstacle or opening in the barrier, that's about the same size as the wavelength of the wave. Then those waves will bend around it. This is why FM radio is not as good as AM radio in terms of range. You can get AM radio stations forever because they've got a really long wavelength, which partly means that they don't get bent by buildings and other objects. Also means that they bounce off of the atmosphere a little bit. Whereas FM waves will get diffracted around buildings and other large objects because those objects are about the same size as the wavelength of the wave. So for us, we're going to talk about particles or sorry, particles do not diffract, but we're going to talk about light passing through two slits separated by a distance comparable to the wavelength, and you actually get an interference pattern. So as those waves pass through, it changes the shape of the wave because they bend. Actually, I think it's the next, yeah, so here's diffraction. So they bend. Now this is just one wave going through one slit. You can see it goes from being the sort of uniform wave. When it hits the slit, it sort of bends and starts to radiate out in all directions from that point. Whereas particle beams, it's just like shooting, I don't know, a paintball gun, airsoft gun or something. They go straight through, right? They're not going to bend around the edges of that opening and hit somebody around the corner. So when you do this with light, so you shine some light source through a slit, through two slits, separated by a short distance, you get two waves happening from the same light source. And so the waves that end up hitting this opening, they bend and start to radiate right up from that point. These waves bend and they radiate out from that point. As those waves interact, because they're coming from two different points, you get areas that are out of phase, which make dark spots and cancel out all of the light. And then you also get waves that are in phase. So you get brighter spots in between the dark spots. And so you end up with this sort of alternating light-dark pattern. And that happens with light. Remember, light is electromagnetic radiation. It's a wave. All right, so there was a thing that scientists observed that a lot of metals, if you shine the right kind of light on them, they start to emit electrons. It's called the photoelectric effect. A lot of light sensors work like this. Shine light on them, it starts to generate a tiny amount of current, and then that current is used to turn on a night light or turn off a night light. It's called the photoelectric effect. Shine light on metals, they can produce a small current. So the original theory for like how this worked was that it was the amplitude that mattered. So basically, if I shine light on a metal, if it's bright enough light, then it'll start to do this photoelectric effect. If I make that light even brighter, then it'll increase the photoelectric effect and you'll start ejecting more photons or electrons. So then the idea also said that if a dim light were used, it would just take longer. Basically, the metal needs to absorb enough of that light before it does finally emit an electron. And that was the original theory. So they went to go test it. So here's some apparatus that you might use for the photoelectric effect. This has to take place, if you want to measure it, really has to take place in a vacuum tube, because then the electrons, otherwise they just get caught by air and get neutralized. But here in a vacuum tube, we can have this terminal, shine a light on this, electrons get ejected, and we can read some sort of current from that light, from that photoelectric effect. So this initial analogy is like this carnival game where you like shoot water into the creepy clown mouth, and then the balloon fills up and then explodes. Even if you use a really weak stream of water, eventually the balloon would fill and pop. Use a stronger stream of water, fills up faster, pops sooner. It turned out that's actually not what happens. So doing more testing, they realized that it didn't matter how bright the light was if it was the wrong frequency. So if the frequency is too low, nothing happens. As soon as you hit the right frequency of light, you start ejecting electrons, and then, and only then, does the intensity change the amount that gets ejected. What do you mean? Yeah. Oh. Yeah. Otherwise, if it's too low, it gets blocked. Oh, interesting. I never thought about that. Yeah. Huh. Really cool. Okay, so Einstein was the first one to come up with a really good explanation for this. And he actually invented this idea. He didn't call them, I think he didn't call it a photon. He said a quanta of light in his paper. But Einstein proposed basically this photoelectric effect was caused by the light acting as a particle. A stream of light has these packets of light called either a quantum or later called a photon. And we can think of light as this stream of particles actually coming from the light source. So then the energy of that photon is directly proportional to its frequency. So higher frequency, higher energy. Lower frequency, lower energy. So basically, you can send more energetic photons if you just increase the frequency without increasing the intensity. So then there was this proportionality constant called Planck's constant that relates the speed of light and the wavelength to energy. Or we could relate it to the frequency. Again, it's a constant. You'll be given the constant. So in Einstein's model, is the rock, the different frequencies of light were like throwing, so if you had a low frequency light, it's basically like throwing that paper at this other carnival game, right? Those milk things are made out of metal, so they're really heavy. Throwing paper at them is not going to knock any of them over. So by increasing the frequency, you throw higher and higher energy things like throwing rocks instead of throwing wadded up paper. And those have enough energy that they can start knocking over the milk bottles. One photon at the threshold frequency has just enough energy to dislodge a single electron from the metal, and then if you increase the intensity, then you're just throwing more photons. A higher frequency photon, it absorbs enough energy that it's able to escape. And so then that energy, excess energy, becomes kinetic energy, and that's why the electron gets ejected. So basically now I'm saying light behaves like a particle, like these photons. But what did I say it was before? It was a wave. A wavicle? That's nice. It's a lot more concise than wave-particle duality, wavicle. Okay, so let's say we've got some metal. It'll eject electrons from its surface when struck by yellow light. So what will happen if the surface is struck by ultraviolet light? So if we look at these one at a time, for A, no electrons would be ejected. Would no electrons be ejected? No, because ultraviolet light would be somewhere over here, higher frequency than yellow light. So electrons would be ejected and they would have the same kinetic energy as those ejected by yellow light. Where does the kinetic energy of the ejected electron come from? Yeah, it comes from the energy of the light. Yeah, so it'll have a greater kinetic energy, not the same. So it has to be C and not D either. Yeah, because this is wavelength. There's the inverse of frequency. So this is a lower, shorter wavelength. Don't want to say lower, shorter wavelength, which means higher frequency. So waves are closer together, so you get more of them per second. Okay, so sometimes light behaves like a wave. That's why we get interference patterns if you show it through these two slits. Other times it acts more like a particle, as evidenced by the photoelectric effect. And that was really the conflict that was observed in these two experiments, is that when I do this, it's a wave, but then I do this experiment, it's a particle, and only the particle definition explains why it happens, and only with certain frequencies of light. So it has both. It's not like it's one in one situation or one in the other, but you're observing different properties depending on the test that you're doing. One test's going to show you that it's got particle-like properties. The other one's going to show you its wave-like properties, but it has both all the time. As weird as that is. So at some point, Louis de Broglie proposed that particles could have wave-like character in addition to their particle character. So he was one of the guys that sort of put these together as, wait, what if it is just both? It doesn't have to be one or the other. It can have both properties, even though we've never seen anything else have that before. Nature of electrons most clearly in electron diffraction. And then this is a weird thing. The interference pattern is not caused by pairs of electrons interfering with each other, but by single electrons interfering with themselves. So one electron passing through will interfere with itself and will only land on certain parts of a detector, which is super weird. So we're going to look at some of these experiments. Oh, and again, de Broglie relation. Oh, so this is the de Broglie wavelength thing. So he predicted that the wavelength of the particle was inversely proportional to its velocity. So basically these electrons are, or the light is a particle moving really fast, and that's why it has a wavelength. essentially no mass. So they're moving really fast, no mass, and so we can calculate for an electron what its frequency is, or what its wavelength is, based on its velocity, its mass, and Planck's constant. Is that new in there? Or is that, this is its frequency? Oh, but if we know its frequency and its wavelength, then we can find use the speed of light and calculate a de Broglie wavelength for anything, even though it doesn't make sense. We'll get to that though. So if we did this experiment, this is one of the things that I changed. I swapped the order of these slides. If it only behaved like a particle, if we're moving on to electrons now, sorry. Talking about electrons, if they only behave like particles, then shooting a stream of electrons through two slits, you should get two bright spots, right? Just like shooting a gun through two slits, paintball gun, airsoft gun, what have you. We won't see any interference patterns. Of course, what actually happens is you do see interference patterns. Using some probably radioactive source, they're able to create an electron beam and shine those electrons or fire those electrons through two slits and see an interference pattern, which is exactly what you would see with light, right? So this tells us that electrons also behave like waves because we get an interference pattern. Oh yeah, here's the de Broglie wavelength. Maybe it's a little out of order. Damn, maybe I copy and pasted something in at the wrong spot. Okay, so what is the velocity of an electron that has a de Broglie wavelength approximately the length of a chemical bond? Oh, actually, I think I did this because this is frequency. Sorry, wait, say that again? But we get, yeah, because this would be hc over lambda is energy. But yeah, c over lambda is the, yeah, that's what I want. Oh, perfect, okay. So I knew I was missing something with this. Oops. Okay, so we can take de Broglie's, and if this is lambda nu equals h over mass, then the speed of light equals Planck's constant over the mass in kilograms. So this is the equation, or I guess in this case it would just be speed, because we want to know the speed, the velocity of the length of the wavelength. So velocity for electromagnetic radiation, it would be c. For something else, it would be h over the mass. So Planck's constant over the mass. I'm going to come back to this because we have the c equals lambda nu. The c would be the speed of light, but we want the velocity of an electron, which we could probably do this anyways, again, later. There's more that I want to work through that. We'll do it during lab. Sorry, we're going to come back to de Broglie. I wanted to calculate, because this is my mass and my velocity on the bullet train. So we're going to calculate my frequency or wavelength, but later. I think there's some arranging that needs to be done. Anyways, in all of this uncertainty, let's talk about the uncertainty principle. Great transition. High five me. When you try to observe the wave nature of an electron, you can't observe its particle nature and vice versa. So you can only really observe one at a time. So the wave and particle nature of the electron are complementary properties. Again, we've got these two properties. It doesn't mean that they are somehow broken or disjointed. They're just both different properties that work together to show us sort of the actual experiments, the results of the actual experiments. So the more you know about one, the less you know about the other, or I guess the other part of the uncertainty principle is that you can't know, which is Schrodinger's equation, you can't know the velocity and the position of a particle at the same time. You can either find where it is or find how fast it's going, but not know where it is. So when we do these different experiments, again, in the interference pattern experiment, we shine this electron beam, electron source. We're shooting electrons through here. And as it goes through the slit, on the other side where we're detecting it, we get this interference pattern. We do not end up with two bright spots. However, if we change the experiment and we instead detect things, this is one of the slides that I changed, we instead detect these electrons a different way. So in this experiment, electrons are being shot through here. And then as they pass through this, there's a laser, the electron gets destroyed and in a flash creates a flash of light at this point and creates a flash of light at this point. And so when we do, that's when we get two separate bright spots. But we've changed where we're looking for the electron. So here we're looking at it right as it passes through a slit, before it has a chance to interfere with itself. In this other experiment, we're detecting it at this back wall and not as it passes through. So we can do one or the other. We can't detect an electron here and then detect an electron over here at the same time. We can just see the flash as it passes through the laser. In that way, we can observe it. Oh, it's going through both of the slits, essentially, is what that tells us. No interference pattern. Sorry, Heisenberg's uncertainty principle is that the more accurately you know the position, the less you know about its speed and vice versa. So you can know its speed or its position, but not both. And that is a math thing. If you solve the equation for position, then the velocity becomes undefined. If you solve for velocity, then the position essentially becomes undefined. So that creates a problem when we're starting to talk about electrons around atoms. We want to know where the electrons are around the atom, but we can't determine where it is because we don't know its position and velocity. But that's okay because electrons are a lot less, are really just not like particles at all. 613. So which statement best summarizes the uncertainty principle? Yep. It's B. So we can't know both position and velocity. And it's not that we can't know position. It's not that we can't know one of them. It's just that we can only know one at a time. So this again brings us back to determinacy versus indeterminacy. So determinacy, or something that's determinate, means that if we know, because we can know for large things what their position is and what their velocity is, and even what direction that's in. And so we can predict where that thing is going to end up, if you throw a baseball, for example. But for electrons, can't know the position and velocity at the same time. So we have this property of indeterminacy. We can't know both. And so the best that we can do is Schrodinger's equation, which basically predicts a probability for where that electron is. We say it's probably in here somewhere. Where in there, can't say. But that's actually good enough for most things. Oh yeah, so this is in a determinate system. Batter hits the baseball, goes flying. We got the force of gravity. Again, physics stuff. But you can predict where that ball is going to land if you can factor in enough things. And the human eye is actually really good at doing that automatically. So classical trajectory versus quantum mechanical probability distribution map, where the electron, if we're thinking of this electron as a baseball pitch, right here, baseball travels in a straight line, or relatively straight line. It takes some path that could be predicted, and that's what the batter is trying to do, is predict that path and then swing his bat into the path of the ball. Now, if you're trying to hit an electron with a baseball bat, you might see the pitcher throw the electron, but then you just swing. And there is a set chance, a set probability that you're going to hit that. And really, you just want to swing in the highest probability zone and hope for the best. Because it doesn't matter where you see that electron leave from, it will end up somewhere else.
Is there a reason why they act like that?
I guess my intuitive explanation of it would be it's that wave-like property of the electron. So they're not really traveling the space from one point to another. Again, this is like a rough analogy, but it's like a standing wave. So like in a standing wave, you would have something oscillating between 2 points. Maybe this should go, that's terrible too. That's better. So you've got this thing and it's oscillating. So this is like a string. If I held a string here and I move it at the right frequency, then I'll have one part going up, one part going down, and there's a node in the middle. So either the electron is either it's going to be in one of those sort of standing wave areas. That's not exactly why, but that's why. At least a way to think of it. So that's why we say it can be in any of this area because it's not like a 2-dimensional standing wave, it's like a 3-dimensional standing wave. So there's areas where that standing wave is more likely to exist. And then when you measure it at any given point, you might be in a fluctuation. So if this, I guess if we treat this as the electron's path, or the electron itself, let's say that we can detect the electron at a peak. So if I'm trying to figure out where the electron is at any given moment, I basically take a snapshot, and maybe the wave is like this, or maybe the wave is like this, and I'm detecting it here or there, but nowhere in between. Something like that. Or if you think about it like a single standing wave, like a jump rope swinging around, you can only detect the jump rope when it's at the peak. So if you're trying to take a picture, every time you take a picture, it looks like the jump rope isn't there. The electron's not there because the jump rope's not at the very top. Until you take a picture at the very top, and you're like, oh, there it is. You take another picture and it's gone because it's in some other part of the atom. Again, rough analogy. Okay, so it's not that, again, electrons don't have energy, they have energy. So the energy and position are complementary. They do both exist. And we can say that an electron has essentially kinetic energy. And this really goes into Bohr's, the Bohr model of the atom. Oh, sorry, electron with given energy, the best we can do is describe the electron's position in terms of an orbital. Again, that's the probability distribution. And we'll talk about those shapes and angular momentum and all of those quantum numbers. But for now, we're just going to talk about these energies and how they relate to different orbitals or where they might be found. So Schrodinger's equation allows us to calculate, again, the probability. So this is what gives us all the different shapes of different orbitals. It's predicted by Schrodinger's equation for different energy levels. And we got a bunch of different wave functions. And basically, we're describing the wave-like nature of the electron, and that's where it is. So we can plot that out and represent our orbitals in 2 dimensions. Oh, that's like the thing that we're going to talk about later. This might be a good spot to stop at then. Yeah. I know it's a little bit early, but we're going to stop there.